It's 6 o'clock. Hello, everyone. I think we should start with the evening lecture. And it's my pleasure to introduce Professor Niccolò Cesabianchi, who is a professor at the Department of Computer Science at the University of Milan in Italy. His research interests include a wide range of fields in the fields of machine learning and computational learning theory, such as reinforcement learning, game theoretic learning, statistical learning theory, prediction with expert advice, and bandit problem. He is a co-author of the books Prediction, Learning, and Games, and book Regret Analysis of Stochastic and Non-Stochastic Multi-Armed Bandit Problems. Today, Niccolò will be talking about learning theory, and we're all very much looking forward to your lecture.
Thank you very much for the nice introduction. I hope you all are hearing me well. It's really a pleasure to be here in my bedroom. Well, okay, and I really wish to be, in Tübingen, but I think this is a pretty reasonable solution that we have to, to undergo these days. And I'll try to do my best, although it's a very different feeling rather than being in a classroom full of people. So there's a little less energy, but I'll try to, to be as entertaining as possible. And so the title of the lecture is Learning Theory, which is the vaguest possible thing. I put on some, I added some words like some elements of learning theory, because at least you have an idea that I'm not going to cover the entire spectrum of learning theory, which would be too much in 2 lectures. And but I will choose a few topics that are, of course, topics that I know well, hopefully, and I think are also interesting and possibly important these days. Okay, as I was discussing before with the moderators, feel free to interrupt me during the lecture. Don't hesitate, and use the raise hand tool or the Q&A window in order to ask questions. So my idea would be to keep the presentation as interactive as possible, given the interface. And we can, if there are too many questions, I don't know, this could be possible, but maybe some of these questions can be deferred at the end of the talk if there are too many interruptions. But usually, I mean, I'd be surprised if you were going to overwhelm me with questions. But don't feel free, please, to ask anything you want to ask. So right, the idea. So what are the contents here? So this is going to be a sort of a foundational lecture, in the sense I'm going to cover some foundational topics in learning theory. As I said, the learning theory is a very broad field, and I'm going to focus on certain aspects. And first of all, I'm going to spend a few words on introducing the field of statistical learning, which is one of the standard models for the theoretical study of learning algorithms. And I'm not going to, dwell too much on this. And maybe, many of you have already a good knowledge of this, but I would like, nevertheless, to start from statistical learning, because it's fundamental. It's again the reference standard model for the analysis of learning, and it will also serve me as a reference for what comes next, which will be a shift from the statistical learning framework to a different framework, which is sometimes called online learning, and is also called sequential decision making. This is a different, if you like, a reference model for the study of learning algorithms that is gives different vibes or give different kind of outcomes. You can think of machine learning as a sort of a phenomenon, like something that exists in the world of machines. And you can, so you can study this phenomenon using different lenses, using different viewpoints. And so statistics is one of them, but it's not the only one. You can also use a different viewpoint and draw different conclusions. And these different conclusions will help you to have a broader perspective and also to understand different aspects of what we call machine learning. Okay, so from then I will move to something which is a kind of abstract decision-making model, which is called prediction with expert advice, and has as variant or extension, if you like, that of multi-armed bandits. Multi-armed bandits is a pretty simple and abstract setting, and but it is also at the basis of more important and general frameworks like reinforcement learning. So you can think of multi-armed bandits as a one-state version of reinforcement learning. We will. So one of the features of the way I will present multi-armed bandits is that I will describe this in the setting of in the so-called non-stochastic or adversarial setting. This means that we will strip out all the probability in the model and only use probability inside the algorithm. I view this attitude or this approach kind of refreshing, especially if you come from computer science, as I do. I'm not a statistician, so I started out in doing statistical learning, and it was really difficult for someone like me who didn't study, statistics in mathematics, in a mathematics program. So I had to go back and learn a lot of things that were sort of not taught in a computer science probability course. And but then I figured out that I could use my algorithmic skills and my computer science skills to do machine learning from a different viewpoint, which is exactly this online learning viewpoint. And this I discovered after some time. So I already did the stuff in statistical learning. And then I sort of enjoyed a lot the possibility of, addressing machine learning problems without having to use statistics. So this is something we will look in the first lecture, and then we will move on in the second lecture to what's called online convex optimization. So online convex optimization is really sort of a broad and general framework for studying online learning and online learning algorithms, and it has a lot of applications, different applications that, for instance, in stochastic gradient descent, and in other areas like streaming data analysis. So we will spend a fair amount of time in our second lecture on this topic, and then after we will move on. Afterwards, we will spend a little bit of time on the topic for contextual bandits, which is sort of a marriage between online convex optimization and the multi-armed bandits in its most abstract and basic way, which we were going to see in this lecture. By the way, I used to give these lectures typically on the board, And because it's mathematics, it's theory, and I find it more respectful towards students if I, if I draw stuff on the board. So I force myself to give to go at a decent pace, and the student will have the time of taking notes. This time I decided to do it on slides. I tried to use animations as much as possible, but it could be the case that I grossly underestimated or overestimated the time it takes to give the lecture. So, well, I apologize in advance if should this happen, which means that in one case I won't be able to cover everything. In the other case, we will be left with enough time to tell each other jokes. But we will see. We'll see. I will try to, to give myself a reasonable pace, and in order to do things, to give each topic the time it deserves. Okay. Right, and one thing, we will do some short proofs. So yeah, I think it's important to, once you do the theory and you explain algorithms and you explain the results, the mathematical guarantees that you have about these algorithms, it is important to be able, whenever you can, to demystify the formulae by showing them showing the derivation. And one advantage of the adversarial online learning setting is that many proofs are reasonably short, so that I can be bold enough to try to explain them over the slides. Usually in doing a proof on slides, it's a pretty bad idea. But doing a theory without showing any proof, it's also a bad idea. So I'm trying to strike some trade-off here and show things that are simple enough so that you can see, now I see how this thing can work. So maybe I can try to figure out also a bit of the things that weren't shown in every detail. Okay. So let's move on. So we see two nice guys here. So maybe you will recognize some of them. You can try to guess before I move on and show the names. Use the Q&A window. Okay, one is a Turing Award. The statistical learning is one of the most important mathematical frameworks for the analysis of learning algorithms, and mostly, let me move the window here so that mainly supervised learning algorithms, okay? So this was pioneered by Vladimir Vapnik in the 70s. This is the first guy you see on top of the slide at the left. And he worked in the Soviet Union by the time, and he somehow started to study pattern recognition, which was the name of machine learning at the time, from a viewpoint of what kind of conclusion you can draw once you have a finite sample of data. So you have to understand that most of statistics at the time was asymptotic. So you would have results of convergence as the number of data points went to infinity. And these things weren't not useful in practical problems, because in practical problems you have finitely many data. And so Vapnik and his co-authors, most notably Chervonenkis, pioneered the study of finite sample statistics in the area of pattern recognitions. So essentially, what happens if you minimize the training error? using in some class of predictors, and you use a certain amount of data. What kind of guarantees or statistical guarantees you can have on the performance of your predictor? So this was very important because it gave us some usable results. It gave also guidelines to practitioners. And it is interesting to note that a little bit later, but independently, because we were still in the Cold War, so there was not a lot of communication between US and Soviet Union in terms of scientific exchanges. Yeah, Vapnik, that's right. Okay. Les Valiant, the Turing Award a few years ago, introduced it in a seminal paper called The Theory of the Learnable in 1984, introduced the field of computational learning theory. So computational learning theory was essentially a version of the statistical framework pioneered by Vapnik, but it was sort of a specialized in a certain sense because it was only looking at certain special cases that Vapnik studied in more generality, but it was also broader in another sense because Valiant understood the importance of the computational efficiency of the problem. I mean, so there are two kinds of resources that you have. One is the data, and the other is how much computation you can spend on the data. Okay, these are two equally important results. So if you have some results that is good in terms of that uses a few data points, but the computation is just exponential, maybe in the number of features, then there's not much that you can do about it, right? And so this was an extremely important viewpoint when it was introduced. And of course, what happened is that these two viewpoints came together at the end of the 80s, beginning of the 90s. So Vapnik started to get invited because now the 89, the Cold War was over. So Vapnik got invited in the main conferences in learning theory, and he told us, look, you guys, what you did so far is very nice, but I did it 20 years ago or 15 years ago. And this is what you should do next. And he pointed at some other directions. Of course, I'm oversimplifying here. It's a lot more complicated, and there were contributions on both sides. And but this is true that starting from the 90s, people understood what the Russians and the Soviets did earlier. And then the abundance of digital data started to kick in. We started to have decently large data sets. And so we started to study principled learning algorithms, right? So indeed, if you want to point out what are the main contributions of, at least in the first, up to the end of the 90s of statistical learning, first of all is the mathematical model of learning, within which you can study what is a good learning algorithm. You can distinguish good learning algorithms from bad learning algorithms from a theoretical viewpoint. And then you can also study the condition characterize what can be learned. This means that if lacking this condition, you can really, I mean, you cannot have much hope that that a learning task can be solved. Even if you have an unlimited amount of data. Okay, so this can sound weird, but there are mathematical conditions ensuring that your learning problem can be solved given a sufficient amount of data. Okay, other contributions are these mathematical models, and the study of the mathematical models gave as outcome a set of guidelines to practitioners. So before that time, people doing machine learning was doing mainly heuristics and playing with heuristics, and there were a few theoretical results, but they were referring mainly to algorithms that you wouldn't use most of the times in practice. There were some isolated results especially for nearest neighbors, for the nearest neighbor algorithm, but there was no systematic framework for the study. So using statistical learning, people understood the notion of learning bias, which means how the choice of your model class is going to, for instance, I'm going to pick a certain class of architecture of neural networks, as opposed to a certain class of linear predictors with a certain kernel function. How the choice of the learning bias is going to affect the outcome of your learning process, and especially the interplay of the learning bias and the overfitting. So one of the major contributions of statistical learning were to give a sound and mathematical, well-founded explanation of the phenomenon of overfitting. Okay, this was extremely important because people now, from then on, they had guidelines that were not down really to the level of how should I choose this hyperparameter, not quite there, but they sort of gave them a sound theoretical framework within which things could be, experiments in machine learning could be carried out. Okay, and there are some examples of principled and practically successful algorithms that were derived as outcomes of the statistical learning framework, especially support vector machines, which were directly derived by designed by Vapnik in the 70s, and then generalized with the use of kernels later on in the early 90s. And then also the boosting framework, which was introduced in the early 90s by Freund and Shapiri, and then now is also one of the main tools in the use of machine learning. And both SVMs and boosting are principal algorithms. They are studied and understood under mathematical conditions, and they have mathematical performance guarantees. Okay, so let me just go on and give a very brief introduction just to give you an idea, because then I will relate to the statistical learning framework later on when I will when I will introduce the other, the online learning stuff. I can see I won't be left out of slides. Okay, I'm going slowly enough. All right, so we have a data space, which is the space where our data points come from, which is typically the d-dimensional real space, because we typically have features, vectors of real features. This is not always the case, but for now we will assume this is the case. And then we have a label space, which is what we want to predict. We can be real numbers if you have a regression task. It can be a binary set if you have a binary classification. It could be any finite set if you have a categorization problem. Okay, we'll keep things simple and just to look at a few examples. One important ingredient is the loss function. The loss function is a sort of a way with which you are telling your learning algorithm whether it's doing good or bad, good or bad, right? So it is really important to pick the right loss function, and it's not necessarily the loss. Okay, you can have a, there are subtleties here. So you can use a loss function to train your algorithm, and then use a different loss function to test your algorithm, because it turns out that this is the best. But in general, we will assume this is the loss function that you use for testing the performance of your predictor. And these are some examples, like the very famous loss functions like quadratic loss, the 0-1 loss for binary classification, and the hinge loss, which is a function which is a convex proxy for binary classification, because the indicator function, that's an indicator function that I'm showing here. I hope you see my pointer. This is, of course, is a discontinuous function, so it's very bad if you want to optimize it. So you typically use convex proxy for binary classification, and the hinge loss is one of them. It's not important exactly how it looks like at the moment. It's just important that you have a variety, a zoo of loss functions that you can use. So a predictor for right now is just a function which will be implemented by some computer program. There's some computer code which is mapping data points to labels. I can use it for classification. I can use for regression. I can use for categorization, whatever I want. And the training set is just a multi-set of labeled points. We will call S typically a training set. Okay, this is what you use when you have a learning algorithm. So what is a learning algorithm? So if you you decide on a loss function. Now a learning algorithm, you can also have this sort of a black box view. It's just a mapping between finite training sets, which are given as input, to predictors, which are given as output. All right. So predictor is mapping data points to predictions, and the learning algorithm is mapping training sets to predictors. Okay, so you have a very simple and schematic setting. Then you say, okay, statistical learning, what is that? So a learning problem is defined by some unknown distribution, D on the examples. Examples are the pairs of data points and labels. And so now in statistical learning, what you assume that any data point is the realization of an independent random draw from this distribution. So anything you observe, any data point you observe in your training set or in your test set, you view it as coming from this unknown but fixed distribution that is lurking in the background, which you can put your hands on. Okay, so this is a pretty strong assumption. First of all, because you assume that data are generated by a distribution. Then you assume they're generated with independent draws, and then you assume that this distribution is fixed. But this is a way of coming up with a clean and usable, tractable mathematical framework. Of course, all of this is just a mathematical model of how the training of a learning algorithm takes place. Nobody is pretending this is actually what happens in practice, but we know that mathematical models are unreasonably good at, they are effective in ways that we cannot really explain. So even though these assumptions are clearly violated in practice, firstly because there are no probabilities in practice, things happens because we are going around and collect our data, and this is far from being an IID process. Even though this is clearly false, the algorithms and the reasonings that we can do are, to within some reasonable extent, applicable to practice. They will deliver results that are meaningful in practice. So this is quite interesting. So once you have these assumptions, and I'm also telling you that you have to choose, of course, a loss function, and this is more a design, so it's not part of the learning problem. It's more like a design choice. So you want to, is like, I think this is an interesting loss function for my problem. And my data is, okay, is being generated by some distribution that I typically don't have any control on. Okay, so now your data is a random sample. That's very good. And but what is in, so given that your data is a random sample, you can use everything you know from statistics. You can throw all the statistical books that you have at your random sample in order to make it confess. And you can really, this is where the statistics kicks in, because you're training set a random sample. But you cannot do that unless you have this, you know, mathematical assumption. You have statistical assumption that you're making. So how are you going to score now your predictors? That's the only important notion, the single only important notion in statistical learning is that of the statistical risk. So statistical risk is the expected loss of a predictor F on a random example drawn from the distribution. Okay, so that's the typical loss, maybe square loss, or maybe the probability of making a wrong binary classification, so making classification mistake if you're using a 0-1 loss, okay, on a random data point. So this is how in statistical learning your predictors are going to be evaluated. So this is the only important thing that you have. Okay, of course you cannot measure your risk because you don't know the distribution, but what you have is the test error, is the test set. And if you use your test set in a proper way, in terms of a statistically proper way, then your test error is going to be a good estimate for the risk. Okay. But I'm interested now in defining the notion of Bayes optimal predictor. The Bayes optimal predictor is the predictor that minimizes the conditional risk, which means that basically is given on every single data point is given the best possible prediction, which is just a prediction that minimizes the risk conditioned on that data point. Okay, so the Bayes optimal predictor is now the best you can possibly do given your unknown distribution defining the learning problem. Okay, so unfortunately, the Bayes optimal predictor can be unreasonably complex, can be, remember, you're typically working in a high dimensional space of feature vectors. And the Bayes optimal predictor can be a very, very complicated function defined over that data space. Okay. Nevertheless, that's the best you can do if you make prediction using labels from your label set, the label space Y. And then you can define the Bayes risk. And the Bayes risk is just the risk of your Bayes predictor. So why is the Bayes predictor making a mistake? Well, typically because data, once you fix the data point, the label can be still stochastic, right? It's true. I mean, if you're doing you're classifying news items, okay, typically not all the people will agree on what is the right category for the news item. So people will have different opinions. So there's going to be a distribution of categories for every given news item. Or you can also, data labels are stochastic also because data points, the feature vector is too little information to uniquely characterize the label. Typically think of weather prediction. Weather prediction, what you do, you make measurements, and then you try to predict the whether it will rain or not, given your set of measurements. Of course, your set of measurements is way too limited that you uniquely determine the weather, which is a very complex phenomenon. So you forget, given your feature vector, weather is going to be a heavily stochastic the event that it will rain or not tomorrow, it will be a heavily stochastic phenomenon. Okay, so even if you knew the true distribution from which data is extracted, and you could compute the Bayes optimal predictor, you would still incur a baseline, an inherent error, which we call the Bayes risk. Okay, so for instance, in the case of square loss, the Bayes optimal predictor, many of you already know this, is just the expected value of the label given the data point. So it's the so-called regression function, all right? And the Bayes risk is just the expected conditional variance of the label given the data, okay? Which is not the variance of the label, because expected conditional variance is not a variance, okay? And if you do 0-1 loss, okay, so your best prediction depends on this function. This function is just measuring is the Bayes prediction always a function, or can it be live in equivalent spaces as L2? Well, not in hypothesis spaces as in parameterized spaces, or okay. I'm not sure you are. It always. What do you mean? It's always it's always a function from data points to. I assume you're reading the question right. So if you're looking at supervised learning, so we are looking at label spaces and data spaces. The Bayes predictor is going to be a function which can be a discontinuous, crazy, complicated function, but it will be a function from data points to labels. If this what you mean? But I'm not sure I got the question right.
Nicolo, sorry,
Yes?
just very briefly. So the students cannot see the Q&A. So could you slowly repeat the question once again, please?
Oh, I'm sorry. Okay. So maybe you can give the mic to the student, because the question was not fully clear to me.
Yes.
If he wants to.
Yeah. Give me a second. Yeah. What's his name, Mijong? Yeah, got it. Yeah. Okay. So, Pierre, you may speak. Pierre, you want to ask your question?
Yes. Sorry, I really did not wish to interrupt. I just asked the question and you did give the answer.
Oh, okay, wonderful. Okay, yeah, just because, okay, good. So the question is if the Bayes predictor is always a function, or it can live in equivalence spaces, say L2. I have not seen yet hypothesis spaces other than parametric spaces, neural networks, or RKHS. Okay, so we won't see, we actually will keep it on a pretty abstract level here. I will give from time to time some reference to specific hypothesis spaces, but for now, let's keep it abstract. So let's see, in the case of 0-1 loss, the important function is just the probability that the label, the 0-1 loss is for binary classification. So the important function here is just the probability that the label is going to be 1 if given the data point. And the way the best you can predict, if you have to predict something deterministic, is just by predicting 1 if the probability of seeing a label 1 is bigger than half. This is obvious. And it should be also obvious then your Bayes risk is the minimum between eta of x, and minimum of is the expectation of the minimum between eta of x and 1 minus eta of x. All right. So again, both these quantities are typically non-zero, which means that even if you could predict even if you knew the true source of the data, you would still incur an error. Okay. So let's now move on to what is known as the bias-variance decomposition, which will be, it's sort of the key to understanding the interplay between overfitting and underfitting. So now let's suppose that we have a predictor, some predictor output by some arbitrary learning algorithm with a training set S. And you have to understand that the predictor itself is a random variable because the training set is a random sample. Okay. So now you can write this very simple decomposition. It's just trivial. So you can write the risk of your. So this is a random variable because it depends on the random training sample. So you can write the risk of the predictor generated by the algorithm as the difference between. Okay, I forgot to say something here. So I am assuming that this algorithm is always picking some predictors from some fixed class, which could be, all the predictors which I can implement using a certain neural network architecture, or maybe all linear predictors in d dimensions, if you like. Okay, so now the best the algorithm could do is to output the predictor of smallest risk in the class. You can only pick predictors in a given class, so the best you can do is pick the predictor with smallest risk in the class, because we said we care about risk. And in general, it won't be able to do so because it doesn't know the distribution D, so it cannot compute the risk, but he only knows some training set S. So there's going to be some estimation error, which is the difference between the risk of the best element in the class and what the algorithm actually chose, selected from the class. The second source of risk is the difference between now the best predictor in the class from which the algorithm selects and the base risk. And then we have the third, the remainder, which is just the base risk. Okay, so we now say that so the risk is the sum of these three contributions. Base risk, we cannot do anything about it because even if we knew the distribution, we still incur it. And now we can control these two contributions. One, we call it the estimation error, and it's going to grow when we do overfitting. And this is the approximation error. And this is going to grow when we do overfitting. So the job of a good learning algorithm is to keep these two contributions in check. So none of them should dominate the other. Okay, so there should be a good balance between overfitting and underfitting. So of course, in order to control underfitting, you would like to pick H as large as possible because, F star can be some very weird function. We typically keep some nice class of functions because that's what our algorithms are able to learn. But nevertheless, we would like this class of functions from which, like let's say neural networks, to be of a certain number of neurons with a certain architecture, to be as large as possible in order for this best risk to come as close as possible to base risk. Okay. On the other hand, overfitting, you say, no, wait a minute. If you make this large, then the estimation error is going to suffer because, why? Because estimating the best element, estimating the element with smaller risk in a large class is harder than estimating the element with smallest risk in a small class. So we can, one idea to control the estimation error is to say, okay, I will minimize the training error. My algorithm will minimize the training error in the class, but I want to make sure that for any H I pick, for any H sub X I pick in the class, the training error is always going to be close to the actual risk. Okay. So what I want to do is that my training error is a good proxy for the risk. Then if I minimize the training error, I will be minimizing the risk, and I will get as close as possible to here. And this is what is called uniform convergence. Uniform convergence is a principle that guarantees that training error and risks will be close to each other. So minimizing training error uniformly over an entire class of predictors. So if I minimize the training error, I will be always doing the right thing. Unfortunately, this is at odds with the fact that we want H large. If we pick H large, uniform convergence is going to go badly. So this is what, but we have other ways of controlling overfitting. We can, for instance, we can say, okay, maybe H is large, but I will actually, prefer simple predictors. So I will regularize my training error by giving more preference to predictors in my class that are simple, okay? This relies on a different effect, which is called stability. And you can prove that if your learning algorithm is stable, which is typically you do by regularizing your training error, by penalizing the training error for the complexity of the predictor, you will be able to control overfitting. And for instance, support vector machines can be thought of a stable learning algorithms, because support vector machines are predictors obtained by minimizing a regularized training error. Another way of controlling overfitting, so controlling overfitting is just an approximation, is an approximation task. You know, approximation is fine. Maybe I will assume that base optimal has some regularities, and I will prove an approximation result that my class H come close enough to base risk whenever F star has a certain regularities. But overfitting is tricky because it's a pretty statistical phenomenon. This is a deterministic thing because everything is deterministic, but at this level, things are stochastic because this depends on my training set. So people, in the course of the years, people came up with different principles to control overfitting. So for another thing, it's very cool. You can prove that your algorithm is able to compress the training set. This is something that support vector machines also do, because the support vectors can be thought as compressed version of your training set. If you don't have any noise and if you give me the support vectors, then I'll be able to reconstruct the training set perfectly, okay, in a certain sense. So this relies on the principle that if I can compress the data, it means that I learned something from, I learned some structure from the data. And I can use this knowledge to predict future data from the same source. There's a lot of literature relating information theory, data compression, and learning. It's very fascinating. You won't have time to cover it. Okay, let me just give you, I'm almost done with statistical learning, but let me just give you some little success stories. Characterization of sample.
Excuse me, there is one question. How
Please.
does the double descent fit into this? One of the students asked.
What, double descent?
How does the double descent fit into this?
Okay, this is not covering, this is a simplified version this is a simplified sort of a framework. Is not covering all possible algorithms. In many cases, you know, your algorithm will extend the model class. The H will be a function of the data. Some algorithms won't fit this framework at all. So it's just not meant to cover everything. We will see just one slide on different things, but this is a reasonably simplified vision that captures many instances, and from which we can derive some firm conclusions. Okay. So you will find exceptions. Okay, now one of the most amazing results of statistical learning is the characterization of sample complexity. This is telling you what is the training set size necessary sufficient to ensure that your variance error, your estimation error, this difference here, is at most epsilon, with some good probability with respect to the random draw of the training set, because again, this quantity is random. And amazingly enough, irrespective to D, which you don't know. So from the data distribution. So let me give you an example for binary classification with 0-1 loss. So we are still assuming our algorithm is picking a predictor for a given class, okay? So, and we see that the sample complexity, whenever the predictor picks, whenever the algorithm picks a predictor from the given class H, from against which we're measuring the estimation error, is determined by a simple combinatorial parameter, which is called the VC dimension of the class. This is a structural parameter of your class of hypotheses. If you have a linear classifiers in D dimension, the VC dimension is going to be D plus 1. And there are many other examples. You can compute the VC dimension, provided your class is not your class of predictors, if your model class is not crazy. Okay, so in general, this is called agnostic case in the literature, but in the full in the case D is some arbitrary distribution over the data, and you want to do binary classification with 0-1 loss, it turns out that the sample size necessarily sufficient to control the estimation error with the most epsilon precision epsilon is this much, where delta is the confidence that depends on the probability of the training set, and D is the VC dimension. So this is a fairly, so the constants involved here are not huge. And this is a distribution-free characterization of the sample size that you need. So this is a quite spectacular result that tells you, okay, give me the class from which you're picking your predictor, if you can define that. Then I will tell you how many data you need in order to learn irrespective to the distribution. Okay. In the special case, which was, by the way, this case studied by Valiant in the 80s, which means that the base error belongs to the class of predictors that your algorithm is looking at, and the base risk is 0, which means that you have a deterministic classification problem. So the data, the x's are still random, but the y's are deterministically given by some f star in your class. Then you're gaining a factor of 1/epsilon with respect to the general case. Okay. And this is admittedly, these sample sizes are not incredibly useful in practice, but they definitely tell you something important about the control of your estimation error. And for certain cases, the VC dimension can be infinite, which means that you cannot simply use this class for learning in a statistical sense, which is a fairly general sense. And it's also interesting to know that in the general case, what it's enough to do is to minimize the training error in the class. So empirical risk minimization is okay if you want to control the estimation error in general. And if you want to do it if you want to control in the optimal way in the realizable case, you have to be a little bit subtler. You have to use a majority vote over a certain set of consistent predictors. So minimizing training error in this case is not actually, it won't give you the optimal sample complexity. This was actually discovered only recently, a few years ago. Okay, so this is a very nice success stories. And let me give you, let me go a little bit, wow, I'm really using up my time a lot. So I can see I won't be able to cover a lot. So let me skip a few things here. Let me move on, which was just one slide. Let me move on now to online learning. Okay, so I will actually be using the entire time slot here. So if you have questions, please keep on interacting me, and then we can use the other opportunities to ask the remaining questions. Okay, so now in many situations, though statistical learning lets you down in many ways. Why? Because in many practical situations, your data comes in a stream. Think of sensors, market data that come from user interacting with websites, right? In these cases, new data is being generated all the time, right? Because you're lucky. You have something that is, you have a process that is producing new data all the time. And this model in which you are training on some data set or on some training test, some training set, and then testing generating a predictor and testing it, It's kind of well suited for learning on data streams. Why? Because you know, you're getting your training set, you're training, you're getting a predictor, and then immediately have some new data. So what do you do? Maybe you train again from scratch, adding in the new data, but this is very expensive. You throw the old data, you train on the new data only, but this is also kind of wasteful. So you need a different paradigm. So what you would like to do is that every time you get a new data point, you should be able to, you know, adjust your predictor, your current predictor, a little bit, possibly in constant time, in order to reflect the knowledge that this new data point brought by. Okay, so this is the general idea of online learning. We want to do things incrementally because we want to take advantage of every new information that is being produced by a stream. Okay, so this online learning model was formalized by Nick Littlestone and Manfred Barmouth in the end of the 80s. Here, I don't have a nice picture of Nick Littlestone, so this is the guy on the left is Volodya Vovk, which also developed in Russia, developed a related framework, much similarly to statistical learning. And but this idea of learning incrementally came up in many different disciplines, including game theory and information theory. So this is something that was sort of a present. I already told you that there are many connections between information theory and machine learning. And indeed, one of these connections was exploited to design learning algorithms that were able to work incrementally. So let's examine this online learning protocol from closer. So at the beginning, on day one you have no data, so you have some default model which we assume is some predictor from your class. And now the stream is switched on, so you're gonna get data pouring in, and then every time you get a new data point, you're gonna test your current model on the next data point. And you're gonna find out some loss. Okay, maybe my current model is not able to predict well at the next data point in the stream. And so what I do is that I will adjust it, essentially base it on what was my current model and the new information that was brought by the new data point. And I would like this computation, this update, only to rely on local information. So it would be very bad if I had to retrain from scratch by remembering all the past data in the stream. I don't want to do that. Okay. And another thing is that, well, I would like to avoid the stochastic assumptions on the streams, because I'm biting the bullet in this case. I'm saying, look, users interact in a completely non-stochastic ways. These processes are really non-stationary. I would like to have a way of using incremental updates to deal with the fact that the data is not actually IID. Okay. So this is a bit, we will see if we can be able to do that, but it's something we can definitely start with. So I'm starting with a very bare bone model. It's just an arbitrary stream of data point being generated in some arbitrary way. And I am I'm testing my current model. I'm adjusting my current model as I see new data. So now of course I want to score this. I want to be able to tell whether an algorithm is good or bad. And I introduce a notion which I call sequential risk, which is defined by some convex loss and some stream. Now, so I have some algorithm A, which is an algorithm which is able to work in the online learning framework. So it's able to do this adjustment of my current models. And then I'm just keeping track of the sum of these testing losses, okay? I call them testing losses, but it's a kind of misleading. Let's go back to the model. It's just these losses that I see here, okay? So I would like to measure now how is evolving this sum over time. Maybe at the beginning, these losses will be high because the stream, I don't know anything about the stream, but then I'm sort of getting to learn something about the structure of the stream. So my sum is gonna grow slower and slower, okay? And then I can, just like I did in the case of statistical learning, I can compare the sequential risk of the sequence of model that my algorithm is generating. It is important to understand here that my algorithm is not generating a single predictor, but it is rather generating a sequence of predictors, because it is adjusting predictors, the current predictor, every time a new data point comes in. So my sequential risk depends on the stream and the sequence of predictors generated by the algorithm. And then I'm comparing with the best predictor I could have used for the entire data stream up to time t. Okay, so this is really a sequential counterpart of the variance error we just saw in statistical learning. There's no more statistics, but I'm really interested in comparing how well my algorithm is doing when scored with this notion of sequential risk against the best model, the best single model I could have used in my class. Okay, so it is important that you understand this notion, and it is important to understand that there's no probability here. It's a completely deterministic object that we're looking at, and we call this object regret. So the regret will be determined by the data stream, by the loss function, and by the algorithm generating the predictors from the class H. Okay, so we have now something to work on, which is a reasonable analogon of what we saw in statistical learning. It is something which I can try to control, and I can say, okay, if I have two algorithms that work one on a certain class of predictor, I can compare the regrets to decide which one is better. Okay, and I can do that on arbitrary data streams. Very good. So that typically we would like, on average, my regret to go to 0 as t goes to infinity. So I would like my average loss on the next point of the data stream to converge to the average loss of the best possible predictor in the class. Very much similar, but average is not expected because it's average with respect to an arbitrary process, an arbitrary deterministic process. Okay, sounds fascinating. So indeed, people in game theory were looking at these things. We see here pictures of James Hannan and David Blackwell. So these were people who studied game theory repeated, right? So, and you can think here of like online learning, like you have some nasty guy who is generating the data stream, and you are playing a game against this guy, and the game is, the goal of the game is to control regret, okay? And you can, of course, assume that maybe the guy is kind of stupid, maybe the stream is not that hard, or maybe the stream is completely random, right? But in both cases, you should be able to score well, because even if the stream is completely random, if H is a reasonable class, no single predictor in H is gonna do well on that random stream. So there's some justice here. I competed on something, but if there is structure, then I want to capture this structure as quickly as possible in order to converge to the risk of the better predictor in the class. If there's no structure, then what the hell? Everybody's the same. Even if I predict randomly, no problem. My regret is actually going to be 0, because I can predict random noise as well as any other function, as well as any other algorithm. So now, okay. So now what we want to do here is that we want to replace the data stream with a sequence of loss functions. Okay. So this is just, in order to simplify notation, I am absorbing the data point and the label in the function L, in the loss function. So the index of the loss function will recall us that typically in real world application, this loss function is generated by some data point, is induced by the data point. But from now on, I would like to talk about loss functions rather than streams. So I'm going to have a stream of loss function rather than a stream of data. And this will be the conversion. Okay, so let's, so what I want to do now is I want to move to a pretty abstract setting, because here I will be able to learn, I will be able to study things in a very clear and crisp mathematical setting with very little ingredients. Okay, so I'm assuming here that my model class is just a simplex, which means that my over a set of d dimensions, right? So my H, my predictors here are just probability distributions over d points, over a support of size d, over a universe of size d. And I would like to focus on the case in which my loss is not only convex, but is even linear. Okay, so if I have a linear loss and I predict with a probability distribution, then I can view my loss as, sorry, there is a little typo here, as the loss, as if I had drawn an index from my distribution, okay, probability distribution over 1, 2, 3 up to d. And then I measured the expected loss. So I'm looking at the component of the loss that I drew according to this index. There is a little typo here because the loss is missing, okay?
But, excuse me, we have another question.
Yes.
So the question is, does the loss I need to be convex, or do our considerations still hold for non-convex losses?
No, the loss will need to be convex for online learning because we are in a more demanding setting, if you like. Okay, so if you think of it, we are insisting on efficiency, and if the loss is non-convex, we cannot even find the best predictor, even if we are given the entire data stream in advance, because we would have to solve a non-convex optimization problem. So we will focus on convex losses. Okay.
Okay.
So, okay. So now what we have here is really a problem which we have a set of D options. We are choosing at random an option from a probability distribution, and we are scored with the expected value of our linear loss, which is this, which means it's just, okay, I'm just drawing a component with a certain probability PT, and I'm paying the component, the loss of the component I drew. Okay, so this is called prediction with expert advice. So if you review it again. So I have the actions, which is the dimension of my simplex, and I have this sequence of losses, which is completely deterministic, and I'm just assuming my loss components are in a bounded range between 0 and 1, which is often the case. My losses is bounded, right? And now at every time step D, I use randomization, which my PT, to draw a certain component. And I will incur the loss associated with that component. And then I will get I will observe all the other components, including the one I did at peak. And I will be, sorry, okay. And this will be my feedback, okay. And so I am, again, I am picking a distribution of losses, and I am drawing a loss drawing a component according to this distribution, and I'm going to be scored with the loss component which I picked, which in expectation, it means data will be scored with the inner product between the loss vector and the probability vector I chose. Okay. So we are sort of saying, where's the randomness here? There's no real randomness, right? Because irrespective to what I pick, I always, at the end, I always see the entire loss vector. So, and I'm gonna be scored with the expected loss. So this is pretty a deterministic process at the end, because I have full information of my past loss vectors. I see my past data points, if you like, but I want to minimize the regret over my set of models, which is now the simplex. Okay, so think of investing in the stocks. So these are these stocks. Your probability distribution is a portfolio over these stocks, and then you partition your portfolio over these stocks, and then you see losses, which could be just negative gains of how much is portfolio, how much is stock gained of lost over the course of a day. And this is going to be the expected incremental gain for day T of your portfolio, right? It's completely deterministic, but I like to think as if you are drawing this from a distribution for a reason which will be clear in a moment. Okay, so first of all, if you minimize a linear loss in the simplex, the minimum is always going to be a corner of the simplex. So I can just replace the minimum over the simplex with the minimum over the corners, which are just my D coordinates. So now you see, and then I'm writing this as an expectation because I'm thinking I'm drawing IT from the distribution PT. Okay, that's fine. I'd like to write the regret in this way. So this is just the regret as we defined it, but it's just a special case because I'm working with linear losses in the simplex. Okay, so we can think of it as, again, as a stock market investment, and P being a portfolio over these stocks. Okay, so now the question is, how well can I do in such a setting, right? Well, it seems very hard in a sense because I have no assumptions on the way these loss functions are being generated, other than they are being bounded, right? So I can use a fully stochastic argument to prove a lower bound. And the idea is, all right, suppose data losses are binary and are drawn at random. At this point, with respect to the randomness of the losses, whatever I do, I will always suffer a loss of a half at each time step because I'm trying to predict a random bit. However, there's going to be some coordinate just by random fluctuations. Some coordinate is going to be better than, so it's a coordinate of the simplex is going to predict this sequence better than the others. Okay, so at the end of the day, I can use, I'm going a little bit quickly, I realize here, but I'm dramatically short of time. So, and this is a lower bound argument. So I can use the important point here, I can use a stochastic argument to prove a stochastic lower bound, which then translates to a lower bound for the individual sequence setting. Because if I prove a stochastic lower bound, I can definitely apply a stochastic lower bound to the to a deterministic setting. Okay, this is a sort of a minimax argument. So what is telling me here is that I can see that my regret has to grow at least as the square root of time, as the square root of the number of stocks I have. Okay, so this is the rate that no algorithm can beat. It is still a sublinear rate, right? And this is a sublinear rate is telling me that on average, I'm going to converge. If I'm able to match this rate in the lower bound, I will be able, as an upper bound, I will be able to convert, my regret will be able to vanish at rate 1 over square root of t, okay? Which if you think is 1 over the square root of the sample size, which if you think is like the 1 over epsilon squared that we saw for the statistical setting. So the estimation error in the statistical setting was vanishing at rate 1 over epsilon squared, which corresponding to 1 over square root of t here, because that's the amount of samples I need to bring down to epsilon the estimation error. So this rate, indeed, I obtained this rate with a statistical argument. So this is telling me, well, if statistics, then of course, I mean, we already know the rate is going to be 1 over square root of t, because you have a very simple, you have a very parametric class. You have just linear losses in a simplex. Everything is simple. So what are you asking us? But will I be able to match this rate without any statistical assumptions? So the idea here that there is a very simple algorithm, which is called Hedge, which is able to match this rate, including constants, which is quite amazing because the lower bound is asymptotic, but I'm going to match this rate at any for any finite d and t. So the idea here is that you have to use randomization. Okay, we said that we are playing a point in the simplex. So what we have to specify is the probability distribution over the simplex. And this has to be dependent on the loss vectors I saw before. So the idea, it's online learning. So we see these loss vectors and we adjust our probability distribution, which we use to pick our action I sub t. Okay, so this is our PT. How do I adjust our PT? Okay, we use it this way. So essentially, we use an exponential distribution, which is which gives to probability to coordinate I, to stock I, if you like, a probability of being picked, which is inversely proportional to the cumulative loss of stock I up to this point of time. Okay, I observe these losses. I can keep track of them, and it is amazing that this very simple algorithm will be able to match exactly the lower bound, including constants, without any statistical assumption. Wow, this is quite amazing, right? So we would like to see this in action. Would like to see the analysis of that. And I'm going to show you the analysis, but I would like to show you the analysis in a broader context, which is the context of bandits. So we will take two birds with a stone, I guess. And we will prove this in a more general setting. And we will prove a pretty general result, which will hold both for bandits and experts, and even in more general. So this is a pretty simple result. Unfortunately, I won't be able to do it entirely today, so we'll use part of the next lecture to do that. And so the idea here is that, well, in some situations, you're not so lucky. And you have long-line learning problems in which the amount of feedback you receive is limited. Okay, so for instance, assume now that you're playing the same game as before, but after you picked an action, the only information you see is the loss of the action you picked, of the coordinate. I'm using coordinate and action as synonyms here. Okay, so now randomization really matters, right? Because the feedback you receive depends on the random realization of your probability distribution. So you draw something with your probability distribution, you observe something, and this is also going to be your feedback. Okay, so it's just before, it's like before, but before I was able, after I played, I was observing the entire loss vector. Here I'm only observing a component. So now the idea here will I be able to sustain the same learning rate which I promised before? Okay, so if you think this is like, so the stock market was the perfect example. In this case, ad placement is a perfect example for bandits, because I have the possible ads. Some user comes up, I pick an ad, I show it to the user, and the user tells me whether he likes or not the ad. Okay, so I have feedback for the ad I showed to the user. I didn't have any feedback. I don't have any feedback for the ads that I didn't show to the user. And the day after, some new user comes up, and I have a new loss function. Every loss function comes to the new user, and user change it from the day to day. There are many others settings in which this partial feedback setting is paramount, is what you get, right? And think in general of recommender systems, because you only get feedback for the recommendation you made, you don't get feedback for the recommendation you didn't make to the user. So this a nice abstract scenario brings in this theme of partial feedback and ways of coping with this partial feedback. Okay, so we will do this in a bit more general framework. Okay, so now I would like to accommodate both the stock market investment example and the ad placement example in the same framework. So I'm assuming here I have some observability graph over actions. So it's like before, I pick an action, but now I am observing the loss of the action I picked and the loss of the action in the neighborhood of the action I picked. Okay, so the graph is determining which action which kind of feedback I'm able to obtain in my problem. So what has this to do with the previous cases? Well, you know, the click is the stock market investment. Whichever action I pick, I always observe all the other losses. The bandit is when you have no edges. Whichever action I pick, I only observe the loss of the action I picked. But then I have intermediate cases. I have a sort of an interpolation between these extreme cases. Yeah. And this could be useful to model cases in which I have some kind of relationship within actions, like if I recommend this car to a user and the user likes it, I know that similar cars will also be liked by the same user. So if I have a similarity graph over cars, I can have this sort of gain. Okay, so I can do recommendation with additional feedback information. Okay, so it's nice that basically the algorithms remains the same. Yes, yes, please interrupt me.
Yeah, maybe you can stop in a couple of minutes and then we still have some time for questions. When you
yes, of course, I will do that. I will do that.
Thanks.
So let me just, I will give the algorithm and then we'll do the analysis tomorrow, and the analysis will take just 10 minutes. Okay.
Sounds good.
So the algorithm is like before. I will still use exponential weights to determine my probabilities. Here they are. However, I don't have any more loss, the full loss vector. So I cannot keep track of the past losses for every action, because I can only observe an action, the loss of an action, if it is in the neighborhood of the action I played at that time step. Sorry. So now I use an estimate which is called importance weighted estimate. So basically I'm saying, okay, suppose that I do observe an action, the loss of an action, because it was in the neighborhood of the action I played. Of, if you like the other way around, the action I played was in the neighborhood of that action, or even that action. Then I see the loss, and I can divide the loss by the probability of observing it. Why do I do that? Because I want to compensate. So by dividing a loss by probability, I make the loss bigger. But then I say, whenever I don't observe that loss, I give it 0. I'm being optimistic. Oh, I didn't observe the loss of that action at this time step, so I assume that action had lost 0. okay? So this is a very simple estimator, and it is based on the randomization of the algorithm. So this probability here is the probability of observing the loss at time t on the randomization of the algorithm, right? There's no randomness in the way the losses are generated. There's just randomization in the algorithm. So now I want to conclude by observing this. Okay, it's easy to compute the conditional expectation of this loss estimate. What is the expected value conditioned on my past choices of the loss estimate of action I at time t? Okay, you know, if I observe it, this is going to be the value, and I observe it with this probability. But look, this cancels with that, and so I get with the loss. If I don't observe it, then the loss is 0. So I really have an unbiased estimator of my loss. And I can, of course, you know that the variance of the estimator is important when you do things. So I want to compute the variance of my estimator, or let's say the second moment. So it's just the same thing. I just square here. So now I can only kill 1 degree of this thing at the bottom. And then I sum again 0 because I have 0 squared, which is 0. And then I get that. But I know losses are bounded. So here is my upper bound on the variance of the loss, with 1 over the reciprocal of probability. So if I make these probabilities large enough, then my variance will be small. Okay, so tomorrow we will analyze in a few slides this algorithm, and then we will move on to the online convex optimization framework. Thank you for your attention, and I was a little slow, but I think I sort of adjusted, so tomorrow we'll be able to, we will definitely skip some slides, as you can imagine. But let's assume these slides are backup slides.
Well, thanks a lot, Nicolo. This was a very nice talk, and I think it was also very clear, so it's good you take your time. So now we have some minutes left for questions from the audience. And, okay. So someone's just posting a question, which I can read out. But if anyone else wants to ask a question, you can also raise your hand. Use this tool to raise your hand, and then you can speak. So the first question is, can you help us develop an intuition for what the VC dimension is?
Okay, no. No, I'm kidding. So yes, I will do that, even though it was sort of okay. VC dimension is a property of a class of predictors, and it essentially measures the ability of correlating with a random sequence of labels. So remember, VC dimension is designed for binary classification. So let's assume that you have a sequence of data points, and you put on these data points random labels. Then you're asking yourself, will I find in my class some predictor which is, you know, which makes a reasonably small, let's say, a training error bounded away from a half on this random sequence of labels? Okay, well, okay, you know, it's a random sequence of labels. So in expectation, your training error is going to be a half. But if you give me a specific realization of this random sequence, then I might be able to find in my class a predictor which has a small loss. Of course, it's a lot to ask. I need to have many predictors in my class, because if I have a long sequence of data points, my realization of random labels will be a long sequence of bits. It will be hard to correlate well with that. So if I have a large class of predictors, now I will be able to correlate well with random sequence of bits, and my VC dimension will be large. So that's the idea.
Thank you. Are there other questions? Or maybe not for the moment. And we also had some questions during the lecture.
Yes, the VC, okay. Can we say the VC dimension neural nets is finite? Even better, we have a bound on the VC dimension neural nets. Yes, we have a bound, and the bound depends on, there are several bounds on VC dimension on neural networks. And in general, if you like, it's gonna be typically a bit superlinear in the number of parameters. So as I said, in the case of a linear predictor, the VC dimension is just the number of parameters plus 1. In the case of a neural network, which is a non-linear predictor, the VC dimension is superlinear in a number of parameters, but it's between linear and quadratic. It's not more than quadratic. But on the other hand, it is a very pessimistic. So neural networks typically do much better than what VC dimension predicts. So one of the big challenges nowadays is to explain how neural networks and the algorithms that train them are able to control overfitting that better, despite the fact that, much better than what VC dimension predicts. So VC dimension loses out in explaining why neural networks work well.
All right, thank you.
Can I also ask a question?
Go ahead.
So I have like one small question. So basically you, maybe stupid one. So you discussed this two setting when like this is like full information setting and then the bandit setting, right? So it's like quite obvious that in full information setting, like we have more information and then we can update all the LTI. So what?
Absolutely.
So yes. What I'm wondering that, so when we analyze the regret bound, so do we see this this phenomena there that, okay, this full information setting has a better regret bound than the bandit setting?
So yeah, there is going to be a parameter that essentially shows you the trade-off. The parameter will be graph theoretic.
Okay.
So basically, the structure of the graph will tell you how fast you can learn.
I see. Okay, I see. And one more stupid question, maybe. So, with like related to someone asked that, like, what about if the loss is non-convex? So, yeah. Can there be any notion of regret when the, well, of course, this notion won't work, but
yeah, well, what people do is, if a loss is not convex, you are doomed computationally.
Yes.
Okay. So what people do in practice is they use convex proxies for non-convex losses. Okay.
Okay.
And so what you can do here is, okay, I will express my regret in terms of a convex proxy of the non-convex loss. Now you can ask, okay, what if your model is inherently non-convex? So like you have a multi-layered neural network.
Yeah.
Yeah. And then, yeah. Again, I mean, neural networks are a puzzle in terms of statistical learning. Now, if you make the setting even harder because you're not using probability, then you're not going to make things easier. So what online learning can tell you in terms of neural network is the following. I can use online learning to do stochastic gradient descent, and I can use online learning, therefore, to train neural networks. And the algorithms I can come up with in online learning are smart enough to take advantage of to learn faster on training sets. So I'm not using the regret guarantees, but I'm using the algorithmic content of online learning here. We will say something about that.
Okay, I see. Thanks.
So if you like, okay, let's see. AdaGrad is one example. So AdaGrad is an algorithm that is being used to train neural networks. Doesn't have any convergence guarantee, but it is a smart algorithm and has been devised in online learning. So it's very aggressive on the data, and this is good.
Yeah. I see. Okay. Thanks.
You're welcome.
All right. So I'm afraid we have to save the other questions for tomorrow and for the roundtable discussions. So please don't forget about them. And I would like to thank you again for this very nice lecture. And we see each other again tomorrow morning.
Yes. Okay. Don't forget everything overnight. And we see each other tomorrow at 9 o'clock tomorrow. Bye. Bye there. Bye then.
Bye-bye.
Bye-bye.